We've all heard about circuits and their uses in electrical appliances, but what are the main components of circuits and how are they related to one another? Circuits in AP Physics 1 can be confusing at first, as it can seem completely unrelated to any past units you've learned about. And while there are many different circuit components, let's take a look at the three most important quantities you'll come across when it comes to simple DC circuits. As we've learned before, charges in conductors can flow and move freely, and this movement of charges in circuits is known as current. The definition for current is the rate of change of charge per time, or charge divided by time, and it's measured in amperes. But what causes the charges in these wires and other circuit components to move in the first place? Voltage, formed usually by the electromotive force or EMF in batteries, measures what's known as the potential difference across circuit components and objects, and it essentially pumps charges through circuits. The higher the voltage, the faster the charges flow, or the more current there is within your circuit. The last component of a simple circuit is called a resistor. Like the name implies, resistors basically resist current, acting kind of like blockades within a circuit and make less charge flow the more resistance there is. Because of this, resistors actually have voltage drops or potential differences associated with them, and also can dissipate energy in the form of heat or light, but we'll touch on that more a bit later. Now, the equation for resistance is that resistance equals something called the resistivity of the material times its length divided by the cross-sectional area, where resistivity is a property of an object based on factors like composition and temperature. In essence, long and skinny objects have higher resistances, while short, wider objects have lower ones. One final cool thing about resistors is that multiple resistors put in different configurations can be simplified down to one single resistor. In the case of resistors strung together on one continuous line of wire, or what's known as resistors in series, the equivalent resistance is simply the sum of all the individual resistances. Another way to arrange the resistors is what's known as resistors in parallel, or resistors on different branches of wires throughout a circuit. To find this total resistance, use the equation that for resistors in parallel, 1 over the equivalent resistance equals 1 over resistance 1 plus 1 over resistance 2, and so on. These two equations can easily be used in tandem with each other. If you're given a complex-looking arrangement of resistors, some in series and others in parallel, start small and work your way outwards, reducing multiple resistors down to one equivalent one through the equations that we just learned. When batteries and resistors are connected in a closed loop of wire, what we get is a simple DC circuit. The battery pumps charge through the wires, creating a current, which then flows through the resistors to create voltage drops and power dissipation. With this being said, let's take a look at some important equations and concepts needed when dealing with these circuits. I mentioned previously that resistors have potential differences across them, but the equation relating voltage, current, and resistance is actually called Ohm's Law. This equation states that the voltage drop across a resistor is equal to its resistance times the current going through it. Furthermore, the power dissipated by a resistor is given by P, or power, equals current times voltage. Substituting Ohm's law into this equation, we have multiple ways to solve for the power dissipated through a resistor using different variables of the circuit. When looking at an entire circuit, however, we need to also take into consideration two main rules, known collectively as Kirchoff's laws. Kirchoff's junction rule states that the current entering a junction or meeting point of wire must equal the current exiting that same junction. While this makes intuitive sense, it's also important to realize that if there is no junction, or in any length of unbranching wire, the current is the same throughout, regardless of how many resistors or batteries the wire contains. The other part of Kirchoff's laws is Kirchoff's loop rule, or that the voltage drop across any closed loop of wire within a circuit must always equal 0. To express this idea mathematically, we take our circuit loop of choice and work our way around. Crossing batteries from short side to long side is a positive voltage jump equal to the battery's voltage, while long to short is a negative voltage. For resistors, tracing across a resistor in the direction of the current is a negative voltage drop given by Ohm's law, while loop directions opposite to the current are positive potential differences. Let's see these equations and concepts in action with a typical, slightly more complicated circuit used in a past AP exam free response. With a 12-volt battery attached to 3 light bulbs, each with resistance 3 ohms, let's go through the motions of finding the equivalent resistance, currents, and the relative brightness of the bulbs in this circuit. To find the equivalent resistance across the battery, let's make use of the equivalent resistance formulas we learned before. Looking at the small branch with the two 3-ohm resistors in series, these two resistors are equivalent to one resistor of resistance 6 ohms. Next, looking at this equivalent 6 ohm resistor in parallel with another 3 ohm light bulb, we can use our parallel resistors equation to replace these two resistors with one of resistance 2 ohms. Finally, all we have left is our 2 ohm equivalent resistor in series with our 3 ohm light bulb, giving us a total equivalent resistance of 5 ohms. To find the current through the battery, let's apply Ohm's law. Using our values of 12 volts and 5 ohms total equivalent resistance, the total current is 2.4 amperes, or amps for short. However, this 2.4 amps is not the current through every single branch of our original circuit, as the current splits at the junctions. To find the current through these top and bottom branches of our original circuit, we need to apply Kirchoff's laws. While there's many different ways to solve this, let's first look at this junction P. We know that 2.4 amps of current are entering from the left, which means that the sum of our top and bottom currents must equal 2.4 amps as well, according to Kirchoff's junction rule. In addition, taking a loop that traces clockwise around these top and bottom branches, we can use Kirchoff's loop rule to find another equation relating the top and bottom currents. Solving this system of equations, the current for our top and bottom branches are not too hard to find. To find the power through each light bulb, all we need to do is apply our power equation, but more specifically, the version containing only current and resistance variables. Substituting in our numbers, we can see that each bulb dissipates a different amount of power. Actually, these powers correspond to how bright each bulb is, as the energy dissipated is light that we can see from light bulbs. While circuits can be tricky and complicated at times, taking problems like this one step at a time and applying the equations we learned will make the process much more organized and easy to handle. In actuality, there's countless other configurations and other circuit components like capacitors and inductors, but those will be the topic for future classes or videos. For now, you can feel good that you've just finished learning about the components and calculations associated with simple DC circuits.